In this experiment, you will learn about the Michelson interferometer. The interferometer is extremely important in the history of physics because it helped disprove the idea of ether, some kind of invisible fluid that was all around us, and help prove the second postulate of special relativity, that the speed of light in vacuum is the same for all observers. A few years back, a gigantic version of the Michelson interferometer was used to detect gravitational waves, and prove that Einstein was right again in his general theory of relativity. So it's an extremely important instrument to learn. Every physicist should know, and it's very precise. It's a high resolution instrument. So this is the schematic of the instrument. So you have a monochromatic light source, and you have two mirrors here, and you have a beam splitter, which is basically a glass plate with a partially silvered on one side, so it can send some light in. So the light that comes out comes from the source like this. Some of it gets reflected to this mirror, and some of it will go through to this mirror, and they come back, they retrace their position, and when they come back here, they recombine, and they give you interferent fringes in a detector here. So you can make this fringe pattern move. But you can make the fringes move by moving one of these mirrors. Then the path difference changes, and from the number of fringes that move, if you count the number of fringes, you will be able to measure the wavelength of the you can measure the wavelength of the source, you can measure refractive index of the medium, and several other applications. There is a nice online simulator of the Michelson interferometer. I shall link that in the course page. So you will do two experiments here, measure the refractive index of air, and now one of these mirrors is mounted on a stage which allows you to make very small movements. So you will basically have some kind of a platform below this mirror attached to a screw gauge. You will see that in the video, and that screw gauge, when you move the screw gauge, the mirror moves by some distance, but there is a reduction factor. That is, the screw gauge, although much more precise than a meter scale, it still will allow only large movements. You need a much smaller movement. So there's a reduction factor that's called the calibration constant. So you'll have to find out what that calibration constant is, because that's key to any interferometer, because that's what's going to allow you to change the path difference and make this fringe pattern move in and out. So for the first part, to measure the refractive index of air, in one of the arms, so these are called the arms of the interferometer, that's one arm and the other arm. In one of those arms, you basically have a glass cylinder, and this glass cylinder is attached to a pressure gauge, and you have a small balloon in which there's a hand pump where you can just pump in air into the glass cylinder. This instrument is identical to how a BP apparatus works, a blood pressure apparatus works, and the old ones, not the digital ones that you have now. And so if you pump in air, then the pressure inside increases. Then the refractive index of air changes because of the higher pressure, and you can measure the pressure here. So the length of that cell is L, and if the optical path length of one beam changes by one wavelength, then the interference pattern will shift by one fringe. So for a length L, the optical path length is equal to NL, where N is the refractive index. It's easy enough to see why the optical path length is NL. You can figure that out easily because you know the definition of the refractive index in terms of the speed of light and the speed in the medium. So the optical path length is NL for a given length L, and N is the refractive index. Now you can change the optical path length to change the fringe pattern, either by changing the refractive index, or you can change the path length. Now the way you change the path length is to move the mirrors. You can move the mirrors back and forth, but that's not being done in this case. What's happening is we are changing the refractive index by increasing the pressure of air in this region. So that's how the path length is varied here. So if the refractive index changes by delta n, the path length changes by delta nl. Now for a single fringe shift, this delta n will be lambda by L, and for m fringes that move or shift, then delta n will be m lambda by L. So if I now define the refractive index of air as 1 plus Kp, that is K is some constant and the P is the pressure. So this is the refractive index for a different pressure. When the pressure is ambient, then the refractive index is 1. For a higher pressure, I will define my refractive index as n is equal to 1 plus Kp, whereas K is some unknown constant. Then for a variation delta n, I can write it as K times delta P, and I can now rewrite this delta P as m lambda by KL. So I just need to find out for a given change in pressure delta P, how many fringes shift. So then if I plot that, I can I will get a slope. From the slope I can measure this K, and if I plug in this value, I'll be able to measure the refractive index. So there's a video in which you have this data available. You have to take the data from the video. You can see the pressure gauge increasing, and you can see the on one panel of the video, and you can see the fringes move. So for you have to basically take the readings from one pressure to the other, the number of fringes that move, and you have to find out the number of fringes that have moved for a given change in pressure delta P, and you have to plot the number of fringes moved as a function of the change in pressure delta P, find the slope, plug it in here, and calculate the refractive index. So this is the steps are, this is the introduction video for the Michelson interferometer. You're watching that now. So then there is another video where the data is available, where the pressure is increased and the fringes shift. You have to count the number of fringes m with respect to the pressure gauge reading and tabulate it. Then plot the number of fringes moved for a given change in pressure delta P, find the slope, and get the refractive index. Now for the second part of the experiment, so this is the linear stage, and you can see a screw gauge here. It's partially hidden, but you can see the screw gauge here. Now for when the screw gauge moves, the mirror actually moves by a much smaller distance. There's a reduction factor. That reduction factor is also called the calibration constant. That's what you need to find out. So if L is the path difference that occurs when n fringes pass when the micrometer is moved by a distance d, then the path difference is equal to n lambda is 2d. Now ideally, when there is no reduction factor or when there is no calibration constant, n lambda will be 2d. When you move the when the mirror is moved by a distance d, then 2d is the path difference, because the beam goes in one direction to the mirror and retraces back upon reflection. So for a given change in distance of the mirror by d, the path difference is 2d, and that has to be n lambda for n fringes to shift. But because the stage has got a calibration constant, the new equation now is n lambda is equal to 2d delta. So that delta is what you need to find. So you need to determine the micrometer reading every time the fringe count increases by 10. That is, it changes by 10. Find the micrometer reading for a change in fringe count of 10, and then plot 2d versus n. Now the slope of that graph will be used to determine your calibration constant. Lambda is 632.8 nanometers that we are going to use. So that's how the measurement is done. So for the refractive index of air video, there is a separate video where excuse me, let me say that again. For the refractive index of air part, you have a separate video where you have to take the data from the video. For this determination of calibration constant part, you have a separate video where you have to calculate the micrometer reading for every change in fringes of 10. So you have to plot 2d versus n, and from that you have to calculate the calibration constant.